So today's going to be all about acid strength. The problem with the term acid strength is sometimes it can seem a little counterintuitive. So let's remind ourselves, what is our definition of an acid? Something that gives up H+, all right? So this is an H+ donor. So something that gives up H+. So acid strength is really a measure of how strongly it gives something up, which can seem counterintuitive because we think of strong things as holding on to things tightly. So really, acid strength is like H+ generosity. How generous is this acid at giving up H+? A stronger acid will be one that is more willing to let go of its H+. And a weaker acid is actually stingier with its H+. It might give it up a little bit of the time, but not most of the time. All right, so with acids, stronger a stronger acid actually holds the H+ less tightly. So keep that in mind when we talk about acid strength, because it does sometimes seem a little counterintuitive to be talking about something as being strong when it totally just drops its H+. But that's what it means. It's just more generous. So we started way back at the beginning of the year. We talked about, not the beginning of the year, but a couple months ago, we talked about these strong acids. I'm going to say, just to make your life easier, I'm going to just change it to 5 that we're really concerned about. We don't really care about chloric and perchloric acid. If you use chloric or perchloric acid at some point later on in life, it's going to be under very careful conditions, because those are they're very strong acids, but they're also very strong oxidizers. You don't want to mess with them. But these 5, hydrochloric, hydrobromic, hydroiodic, nitric, and sulfuric, are pretty common strong acids. So a strong acid is one that completely dissociates in solution. All right. So we're looking at, HA going completely to H+ plus A minus and not going backwards at all. So if you think about what the equilibrium constant for that reaction is, if at equilibrium all of my acid has dissociated, effectively Ka is what in that case? Infinity. Yeah, Ka approaches infinity. Now, Ka is not actually infinity, but Ka is so high that we can't measure it for these strong acids in water. You can actually measure the Ka in other solvents. But Ka is too high to be measured. So Ka is effectively like it's infinite. Weak acids, on the other hand, a weak acid only partially dissociates, meaning some percentage of the molecules split up at any given point in time, but most of them don't. So Ka, if you look up Ka values, these are usually between like 10 to the negative 13th and 10 to the negative 1. So there is a bit of a problem in our language when the only things we'll call strong are the ones that are infinitely strong, and then everything else is called weak. But we have this really wide range of how weak they are. I wish the terminology wasn't what it is. I wish we actually used some better terms for this. But when we say strong acid, we mean super duper infinitely strong acid. And when we say weak acid, we mean any acid that's not super duper infinitely strong. So it's like, Superman would be strong, and everyone else on Earth would be considered weak. Like even the, people in the world's strongest man competitions who lift buses and stuff, and pull airplanes and whatnot, they would be considered weak because they're not Superman. All right. So our language is, when we say strong, it means infinitely strong. When we say weak, it means anything else. And there can be gradations, from Arnold Schwarzenegger to me, among weak acids. Is there a question? No? Okay. So we will use terms like, oh, this is a relatively strong weak acid, and this is a moderately weak acid, or this is a very weak acid, depending on what the size of Ka is. So there's a big range. So maybe the best way to think of this is by imagining a beaker of HCl versus a beaker of hydrofluoric acid, which is weak. So let's say I dissolve 10 molecules of each. In the HCl beaker, what would I see? All right, it dissociates completely. So what would I draw in the HCl beaker? H plus and Cl minus. I would draw 10 H pluses. Maybe I'll do 5. Make life easier. So if I dissolve 5 molecules of HCl into water, I would get 5 H plus ions, and I get 5 Cl minus ions. If I dissolve 5 molecules of HF, how's it going to be different? All right, maybe I'll still have some HF. In fact, it's probably more like I'd have 4 HFs and only one would split up. You don't know the numbers yet. The numbers we're going to deal with later when we start doing the calculations. But this beaker would probably have mostly HF molecules. And then just a few H plus and F minus ions. So this is the distinction between a strong acid and a weak acid. It's about to what extent they dissociate when they dissolve. Questions there? Yep. The question is, why does HF not dissolve completely? And I want to correct you, because it does dissolve completely, but it doesn't dissociate completely, because it turns out it doesn't. So the last part of the lecture is going to be all about, well, what makes one acid stronger than another or weaker than another. So in this case, the distinction between HF and HCl, it turns out it's going to be the bond strength. Hydrogen and fluorine have a pretty similar have a pretty similar size. They make a nice strong bond. And so it's harder to break that bond up than it is for HCl. Chlorine is a much bigger atom, and it's really hard for it to bond with hydrogen. I usually make the analogy, I'll make this later, of like imagining Andre the Giant trying to hold hands with a baby, right? It's going to be hard for him. It's easy for the baby's hand to slip out of his because it's so big. So hydrogen and chlorine, turns out they have a pretty weak bond, and so it's easier to break. These strengths are actually something you measure in the lab. So we can come up with theoretical reasons for why one thing's stronger than another. But in the end, it's just, well, this is what the measurements say. HF, only a certain percentage dissociate, whereas HCl, they all dissociate. So the question is, are acids considered molecules? So acids are molecular compounds. A lot of them will exist as liquids or gases on their own. So HCl on its own is a gas, but when you put it in water, it dissociates. So these acids are molecules that can exist on their own in an undissociated form. It just turns out when you dissolve them, some of them dissociate, or in the case of a strong acid, all of them dissociate. But they are still considered molecular. Yep. One other thing I want to point out about my picture of HF over here on the right is that, right now I've drawn 4 HF molecules as being undissociated. There's nothing special about those 4. If we were to redraw this picture as a cartoon over time, what you would expect to see is, the H plus and the F minus that I have right now would come back together at some point, while one of the HF molecules that's there would split up at some point. So remember, this is a dynamic equilibrium, so it's not like you can just pick out, well, in my collection of HF molecules, this one's going to dissociate, but the rest of them aren't. It's at any given point in time, a certain percentage will be dissociated, and the rest won't be. But that'll change as they break up and come together in equilibrium in the solution. All right. So for a polyprotic acid, if I were to try to do this, that's where things get really, really complicated. So if I wanted to draw H3PO4, remember H3PO4 is a polyprotic acid, so it has multiple H pluses to give. And if I dissolve, say, 10 molecules of H3PO4, maybe 2 of them dissociate. All right? So I might get a bunch of H3PO4. And then a couple of those might split up into H plus and HPO4 minus. So maybe I'll try and color code here. So if 2 of them dissociate, they make H plus and HPO4 minus, or H2PO4 minus, sorry. And then, maybe if I had 200 H2PO4 minuses, a couple of those might dissociate. But if I'm just drawing, only a few molecules here, at this scale, I'm not even going to get any that dissociate the second proton. So in order to have some of the H2PO4 minus dissociate, I'd have to draw way more molecules. And you can say seeing that third proton dissociate would be even less likely. So we wouldn't even see any PO4 3 minuses unless we drew hundreds of thousands of molecules in there, which we're not going to do. So for a polyprotic acid, really, each successive dissociation gets less and less likely. All right. Any remaining questions about acid strength? All right. How about base strength? Well, what do we mean? Remember our definition of a base. A base is an H plus acceptor, something that can take H plus away from water to make OH minus. So when we use the term strong base, what we mean is that if I add 1 mole of that base to solution, it's going to make 1 mole of OH minus. Any base that if I add 1 mole of it and I only get half a mole of OH minus, we would consider that a weak base. All right. So, this is similar to what we said about a strong acid. A strong acid, if I dissolve 1 mole of a strong acid and it dissociates completely, I get 1 mole of H plus. Here, if I dissolve 1 mole of a strong base, I get 1 mole of OH minus. So the question is, why did I write at least? And I'll explain when I get to the bottom of the page. So the vast majority of strong bases you're going to run into will be metal hydroxides. So can you give me an example of a metal hydroxide? Sodium hydroxide. So NaOH. You put it in water and it makes Na plus and OH minus. Right? So that's your typical example of a strong base is going to be something that already has OH minus in it. KOH would be another example. Now, there are bases that are stronger than OH minus. And if you put them in water, they will completely rip H plus away from water to make OH minus. So one example would be if I put sodium oxide, Na2O, into water. Na2O has the O2 minus ion in it. So O2 minus, when it sees a water molecule, what do you think it's going to do? Take what? Take the H plus. So if I have O2 minus plus H2O, and it takes an H plus away, right? That's going to make 2 OH minuses. So really, Na2O, if I put it in water, that'll make 2 NaOH aqueous, which really will make 2 Na plus 2 OH minus. Which is why up at the top I said at least 1 mole. Because here, if I dissolve 1 mole of Na2O, I get 2 moles of hydroxide. So those are strong bases. Things that completely, 100% of the time will take H plus away from water. And then we can have weak bases. So weak bases reach equilibrium with their conjugate acid. Remember, in this equilibrium, this thing over here, BH plus, is what we call the conjugate acid of the base. So here there will be an equilibrium. And remember, we gave the equilibrium constant for this a name. We said Kb is going to be equal to concentration of BH plus times OH minus over concentration of the base itself. And again, for most weak bases, just like we saw for weak acids, this is usually going to be in the 10 to the negative 1 to 10 to the negative 13 range. I keep forgetting, but I need to make some copies. We have a list of Ks and Kbs that we give you for when you do the problem sets. Comes out of the book. We just make copies of it. So we'll give those out next week. And you'll just have a list of all of these. So for any problem that we do, you can just look up the K or the Kb that you need. Question? So the question is, do strong bases completely dissociate like strong acids? Yes, although strong bases are different in one regard. We said a minute ago that acids are considered molecular compounds because when they're on their own, they're not ionic. So like HCl on its own is a gas. Its molecules of H and Cl, it's not split into ions. They actually have a covalent bond. It's only when you dissolve them that they make ions. A strong base like sodium hydroxide, on the other hand, on its own is composed of ions. And then when you dissolve it, those ions dissociate. So there is a distinction there where, sodium is essentially like a spectator ion when we're talking about acids and bases. These things, Na plus, K plus, they just always end up being spectators. The other thing is, for a weak base, the reaction is not, the reaction of a weak base is not a simple dissociation. For an acid, you have HA splitting into H plus and A minus. So that's what we call a dissociation. It's two things splitting up. Whereas for a base, it's the base actually pulling H plus away from water. So this isn't generally called dissociation. This is called a hydrolysis reaction. Some of you might be familiar with like the roots here. So hydro usually means what? Water. Lysis from biology you might know. To break, yeah. So the base reaction is not called dissociation, it's called hydrolysis because the base is actually breaking water up. All right. So that is a distinction in the language we would use. Unfortunately, there are other reactions that are also called hydrolysis. So it's imperfect language. But such is life. There are lots of reactions where you use water to break something else up, and we also call those hydrolysis. All right. So now base strength is going to be measured by Kb. So we've seen we have Ka, which measures acid strength, and Kb, which measures base strength. So the next question we want to ask is, all right, if we have a conjugate pair, an acid and its conjugate base, what does the strength of one tell us about the strength of the other? So let's think about this intuitively. All right. If I'm an acid, that means I'm an H plus donor. Okay. Now, what if I'm a very generous H plus donor? So I have a proton in my hand, and I'm very willing to just give it away. Once I've given away the proton, what do I become? I become a negatively charged ion, and what do you call me now? Now you call me the conjugate base. Now, how greedy am I going to be about going to grab the proton? Not very greedy. So the more generous an acid is, the less its conjugate base is likely to go grab a proton. In other words, the stronger an acid is, the weaker its conjugate base. If I'm an acid and I'm really kind of hesitant to give up my proton, I'm like, I like my proton, I don't want to give it up, and Giovanni happens to reach out and grab it, now I become a conjugate base, and as a conjugate base now, how do I feel? I really want a proton back, so I'm going to be looking around to grab one. So as a conjugate base now, I am stronger. All right? So on a conceptual level, you want to understand that the stronger an acid is, the weaker its conjugate base will be. So now let's look at it mathematically. Okay? Ka is kind of a mathematical measure of how strong an acid is. Kb is a mathematical measure of how strong a base is. Will there be a relationship between those two numbers for a conjugate pair? And I want to be clear when we're talking about a conjugate pair, right? If I'm talking about HF splitting up into H plus and F minus, the K value for this reaction is the Ka of HF. If I want to talk about the Kb of its conjugate base, what is its conjugate base? F minus. So the Kb reaction for F minus has to have F minus reacting with what? Not with H plus. So for Kb, remember my equation looks like this. So it's got to be the base plus water. So it would be F minus plus H2O, making HF now plus OH minus. So the Ka equation and the Kb equation are not exact reverses of each other. So the K value for the second equation would be the Kb of F minus. So the more willing my acid is to give up H+, the less hungry for H+, the conjugate base is. And we want to look at the mathematical relationship now. I'll give you a moment to finish writing. So what is the relationship between these two? They're not exactly reverses of each other. Well, here's what I'm going to do with the two equations. I'm going to add the two equations together. Actually, you know what? Never mind. I'm going to do something different. All right, so the Ka of HF is going to equal what over what? H plus times F minus over concentration of HF. All right, the Kb of F minus is going to equal what? Concentration of HF times the concentration of OH minus over concentration of F minus. What happens if I multiply these two numbers together? Well, I get H plus times F minus over HF times HF times OH minus over concentration of F minus How can I simplify that? Cancel out the HFs and the F minuses, and what am I left with? H plus times OH minus. Have we seen H plus times OH minus before? Yeah. Where have we seen that? Take a look back. I mean, it's been a while. So take a moment, look back through your notes. See where have we seen concentration of H plus times concentration of OH minus before? Adriana? The equilibrium constant for water, what we called Kw. This is going to be true actually for any conjugate pair. The Ka of the acid times the Kb of its conjugate base is going to equal Kw. So notice what that equation says, which is what's on the top of the page. For a conjugate pair, Ka times Kb equals Kw. Kw is a fixed number at a given temperature. Right? We said at 25 degrees Celsius, Kw is 10 to the negative 14th. So for this equation to remain true, the higher Ka is, what does that mean about Kb? Has to be lower. If Kb is higher, Ka has to be lower. So it's saying mathematically what we just said conceptually. The stronger the acid is, the weaker the conjugate base will be, and vice versa. So the strength is related for any conjugate pair. If you know the Ka for the acid, you can find the Kb of the conjugate base. If you know the Kb of the base, you can find the Ka of the conjugate acid. So for HF, here is the Ka. Go ahead and find the Kb of F minus. Ten to the negative 14th is Kw. All right, I'm going to go with about 1.4 times 10 to the negative 5th. All right. All right, sorry, yeah, my bad. Negative 11. Yep, question. Sorry? Your calculator's saying to the negative 19? All right. So when you punch these things into your calculator, if you're not using that EE button, that shortcut, then you're going to want to use parentheses. Because otherwise what it'll do is it'll multiply by 10 to the negative 4th instead of dividing by 10 to the negative 4th. All right. So let's consider nitric acid. What kind of acid is nitric acid? Strong. All right. Remember, nitric acid is strong. So the Ka is effectively what? Infinity. So for this conjugate base reaction where NO3 minus is taking H plus away from water, Kb here would be Kw divided by Ka. So that's 10 to the negative 14th, a small number, divided by infinity, which is essentially what? All right. What's the moral of the story for that slide? The conjugate base of a strong acid is not a base. All right, so the question is, does it work in the other direction if it's a strong base? Remember, strong bases are fundamentally different from strong acids because a strong base already has OH minus in it. So OH minus, what's the conjugate acid of OH minus? What does OH minus become if it grabs a proton? H2O. So, you know, with a strong base, it's a little bit different. So don't think of strong acids and strong bases as being the same thing. They're fundamentally different. So it doesn't work exactly the same way for strong bases. All right, so main point to keep in mind, We already said, we'll reiterate. A stronger acid has a weaker conjugate base. A stronger base has a weaker conjugate acid. And I can't emphasize enough, I'm talking in relative terms here, so stronger, weaker, because our language sucks. When we say just strong, it means this different thing. It means super duper infinitely strong. So don't get it in your head that a strong acid has a weak conjugate base. We just said a strong acid actually has a non-conjugate base. So always think in relative terms. The stronger one thing is, the weaker its conjugate is. So then the very last thing I want to talk about today is, I mentioned that these K values, well, we might as well put on this side, Ka times Kb equals Kw for a conjugate pair. These K values, Ka and Kb, they tend to be between 10 to the negative 1 and 10 to the negative 13. That's a really wide range. Most people look at numbers like, 3.7 times 10 to the negative 10th. What is your response when you hear that number, like in your brain? What's the first thing that happens? All right, some of you are like, I can tell that's a tiny number. But I think, what's the initial reaction when you see a number in scientific notation? What is going on? All right? Most people, I feel like, you can train yourself to see numbers in scientific notation and, well, I'm a scientist, so I understand that number. Of course it makes sense to me. But most people, when they see numbers like that, the first thing is like, oh, man, I got to deal with that. Right? So most people prefer numbers like 7, 3, 8. So what we do is we use a logarithmic scale. All right? And we're going to see this with the pH scale, but I'm going to introduce it now. Whenever we put P in front of anything, P stands for power in this case. So lowercase p in front of anything for us is going to be the negative log base 10 of that thing, whatever it is. So pKa is going to be the negative log base 10 of the Ka. pKb is going to be the negative log base 10 of Kb. And I'm not going to keep writing base 10. When we just write log, the assumption is going to be that's base 10. And if you don't know much about logarithms, think of it as just that button on your calculator that says log. We'll also see pH will be coming up. That's going to equal the negative log of the concentration of H+. And that's usually about equal to whatever the power is on 10 when you write it in scientific notation. So like, if Ka equals 10 to the negative 5th, then pKa equals 5. So that's where the power part comes from. That's why it's P. Whatever power there is on 10, it's going to be around there. So one of the properties of logs that's helpful, and I think I'll write this on the next slide. One property of logs that's helpful, we know that Ka times Kb equals Kw for a conjugate pair. If we're using pKa and pKb, we just turn multiplication into addition. So for a conjugate pair, pKa plus pKb is going to equal the negative log of 10 to the negative 14th, which is 14. So we're going to have 1 foot in the actual scientific notation realm and 1 foot in this logarithmic realm. You just got to get comfortable working between the two. Now, one of the problems here is that it's the negative log. That negative sign means that as Ka goes up, as Ka gets bigger, pKa gets lower. So it turns out a higher pKa means a lower Ka. And a lower Ka means what in terms of acid strength? Less acidic. It means a weaker acid. And with pKb, we can say the same thing. A higher pKb means a lower Kb, which means a weaker base. On the problem set, you'll end up doing a lot of practice with just getting used to these numbers and being able to do that reasoning. Oh, well, this one's higher, so this one's got a lower Ka, therefore it's weaker. So you just want to familiarize yourself with that. So the last thing we'll do, given a list of acids and their pKa's, I love some of these acids. H2OSO5, that's a fun one. It's got osmium in it. Yeah. So if I wanted to put these in order from strongest to weakest, the strongest would be the one with what in terms of pKa? The lowest. So strongest would be here. And the weakest acid listed would be H2OSO5. And you could put them in order in between. When we see the pH scale, this will become a little more intuitive because I think most people at least have an idea that lower pH means more acidic. So lower pKa also means stronger acid. So those two do go together. All right. And in E-block, I'll be talking about what makes an acid stronger or weaker.